The purpose of this video is to give you an introduction to Hydrus1D. Hydrus1D is software to analyze one-dimensional flow in partially saturated soils. Hydrus1D can solve for water flow. It can also solve for transport of solutes and heat. What we'll do here is just to take a quick overview of Hydrus1D, and then we'll work through some examples that'll show you how to use it. And the examples that we'll do are shown here. These examples really just involve flow that results from rainfall. And we'll first look at rainfall under uniform soil where the rainfall is either greater than or less than the saturated hydraulic conductivity. And then look at redistribution of the water after rainfall and as a result of ET or when ET is present. And then we'll make the analysis a little more interesting by adding a low permeability layer. Hydrus1D is distributed by a company called PC Progress. So in order to run Hydrus1D, you need to find the PC Progress website and download it from their website. So you can search for PC Progress or search for Hydrus1D, and you should go to a screen that looks like this one. PC Progress has a variety of software packages that they sell. Hydrus2D and 3D, for example, are commercial packages, and a variety of others, but Hydrus1D is publicly available at no cost. So we can download it from their website and use it. What you should do is select Hydrus1D, and there's a lot of material here that's related to Hydrus1D. It's very powerful package, so you should take a look at some of this various material. There's a variety of examples here, some detailed descriptions of the program, some things that you can download, and then of course there are other programs that are related. What we're going to do here is to go to the download page right there, and you're going to want to download and install this package here. So go ahead and do that, and when you're ready, we can start up by taking a look at what this program looks like. This should be more or less the screen that you get when you look at, well, what you can do when you first open the program is open one of the example files, and you can do this by selecting File, Open, and then under the should be the default folder called Direct. There are a variety of example files. You want to scroll down through these folders and select these are the examples themselves. The examples are described in more detail on the website, and so you could select these and take a look at them. And I've selected one here that is actually one that I made. It's quite simple. But it shows the kind of things that we'll see when we go to set up these packages ourselves. So these are the different kinds of things that you need to set up, and these are they're going to be the main entries into the setup process for Hydrus1D. There's various types of information from geometry, the time stepping, printing, and then various things about water flow, boundary conditions, and the soil profile. And we'll go through step by step, and I'll show you how those all work. Those are this menu selection. You can see these are repeated here. And in addition, there are a variety of other things, heat transport, carbon dioxide transport, that this program will also do that we're not going to get into in this example, but you should look at these types of things if you're interested in them. So we're going to set the model up with the information here on the left side, and then when we're done, we can run a simulation after we've stepped through all the examples or all the pages that we need to fill in. We can also run it right here by executing Hydrus. And once we do that, we'll have some results, and the results can be accessed right here over on the right side, or here in this pull down menu. Okay, so that's really the big picture. And to show you how this works, let's take a look at an example. So the first one that we'll do is rainfall on a uniform soil where the rainfall is less than Ksat. Now, what I would recommend doing is opening a file that's called Hydrus1D exercise. This is a Word file, or maybe you'll find it in a PDF form. And this will describe in text form how to set up this example. This may be more convenient for you to follow than the video. Okay, so this is just some intro, and what we're going to do is set up this example where the rainfall rate is less than Ksat and the soil is uniform. So this red block here is main process, geometry information, time information, and that corresponds to main process, geometry information, time information. Okay, so this will be just another form. This file will be just another way of describing how to set up the model. Okay, so let's do this. Let's go and start a new model, and we'll call it test case 1. And then I'll put in a description. This will be the example for video. You might call it something else, but this describes what I'm going to set up. Hit OK. And so here's the setup. You can see we don't have any information here for post-processing. That's because we haven't run the model yet. So to start off, we're just going to go through and go through this list here in sequence and fill out the forms. So we're going to follow along those notes in the Word document. And the first thing to do is set up the main processes, and we'll just go with the default, which is water flow, and hit OK. That's easy. Well, let's do this. You can do two things. If we hit OK, then that closes this out and we can open up geometry and hit OK there. But another way to do it is to hit main processes, and then we can hit next, and this will go to geometry information. So just another way to cycle through these different entry screens. So we'll have one soil material, one layer for mass balance, and it'll be vertical. And let's make the depth of the soil layer 80 centimeters. We set the length scale right here, and then we'll hit next. So this is time information. And the simulations that we'll do are going to be rainfalls that occur over a scale of hours. So I think hours would be a more convenient time unit to use. And the first analysis that we'll do will be for 8 hours. So we'll set 8 right there. And then the time steps, this default, it may work okay, but we'll make 10 to the minus 6 be the initial time step, and 10 to the minus 7 be the minimum. And this is going to tend to increase the time steps as we go, assuming the numerical simulation, assuming the numerical calculations are going okay. But we want to limit the maximum time step for this simulation to half an hour. And we will have, yeah, that should be okay. When we do some more modifications, we'll have some time variable boundary conditions. But this first analysis, we'll just consider 8 hours of rainfall. So we don't need to use that. Okay, so next is the print information. We're going to print every hour. And print number of times. This will be the number of times that we want to have output. And so let's, as a first one, put in 5 times, and then we need to select what those are. So these will be like snapshots in time, and what I think will work pretty well is half an hour, 1 hour, 2 hours, 2 hours, 4 hours, and 8 hours. Okay, so that's the setup for the times. Hit OK. And we can go to next. Okay, so this is for the numerical solver. This is the number of iterations. 10 iterations may be just fine, but let's just give it a maximum of 100 iterations. This model runs very quickly, so this will be okay. And then I think we can just leave all the defaults here, at least for now. Okay, so now we've gone through to the iteration criteria, and we're over here at the soil hydraulic property model. And there's a variety of possibilities here, but we want to just go with the simple one, which is the Van Genekten Moalem model with no hysteresis. So these are the defaults, and we'll just hit next. And then these are the parameters for the Van Genekten soil water retention model. This is the residual saturation, and just so that we're all on the same page, let's have a residual saturation of 0.08, and the saturated water content is 0.43, so we can just leave that. Alpha would be 0.015 per centimeter. N is 1.875, and you can take a look at the Word document and find these numbers there. And this is the saturated hydraulic conductivity, and we'll just put that as 2, and this term L, we'll just leave that as 0.15. Okay, and then this stuff we don't need to use that for now, so we can hit next. And now we're going to set up the boundary conditions. So we'll go with a atmospheric boundary condition with surface runoff. Okay, so this will allow us to have rainfall, and the boundary condition will switch. If it's a light rainfall and the surface is not saturated, then we'll have all of the rainfall infiltrating. But if the soil becomes saturated, then we'll switch and have the boundary condition hold the surface saturated, and we'll then also be able to calculate runoff. Okay, and then let's see, at the bottom, we'll just have free drainage out the bottom, and the initial condition we'll specify in pressure head. Okay, so we have time variable boundary conditions, and we've got an 8-hour simulation. So this is the boundary condition from 0 to 8 hours, and we'll have a precipitation. For this case, we've got to give the precipitation value. So we'll have a rainfall. Remember, this is a case where the rainfall rate is less than the saturated hydraulic conductivity. So let's have a rainfall rate of 1, evaporation rate of 0, and then this H crit we can have as, we can just leave that. So I'm going to go back and check this. Let's see. Okay, that's good. So Ksat of 2 and rainfall of 1. So that's what we want. And we're getting there. So now we're down here, and we want to set up the conditions in the soil. So we'll take a look, and we'll use this profile application. So hit OK, and now we're going to save the data. So yeah, say yes. And so you can look down here, and there's Hydrus1D, and then down here this is another window that we've opened up, and this is the editor for the soil column. So here's the soil, and then these are this is a uniform material and everything's uniform here, but we'll see as we get a little more complicated examples that we can edit this and make it non-uniform. But what we're going to do right now is just use it to set the initial conditions. So go over here to conditions and go to initial condition and pressure head, water content. Now if we hit edit, then we can go over here, and I'm going to go on these horizontal lines and then hold the mouse down and just kind of paint them like that, and then go all the way down, and then I go over here and left click, and when I left click I get this window, and these are the initial pressure heads, and I'm going to set them equal to -500, so it'll just be uniform equal to -500. Hit OK, and you can see it shows up there, and good, that's what we want. Okay, so we can close this out, and we'll save the changes, and we want to overwrite everything, and then this is the last window that we're going to get before we run it, and this shows just the this is a spreadsheet form of the setup data. So there's the depth, there's the H, the initial head at -500, and here's the material. It's all this stuff is uniform, but we can scroll down here and take a look at really the only thing that's changing here is the depth, but that's okay. This will be more complicated as we move on and look at more detailed models. Okay, so that's the setup. When we hit next, then it asks whether we want to run Hydrus, and we'll say okay. And this is the output from the Hydrus model itself, and we're looking for this. Calculations have run successfully, and so that's good news. And we'll press enter, and then we have results here that show up over on the right side. So we can take a look at the profile information, and the first thing that we get is the pressure head. Here the x-axis is pressure head and z-axis is depth, and you can see that we've got these different profiles. These are at different times, so we might want to add in a legend, make it visible, and say on the bottom right. And so yeah, it's not the greatest thing, but how about there? So this is these T's correspond to the different times that we set up earlier on. So we can look those up and find out what times they actually are, and so that would allow us to help diagnose what these different profiles are. But I think it was like 0.5, 1, 2, 4, and 8 hours. Okay, and what we can see is we have this wetting front. It's moving down with time, reaches about 40 centimeters after 8 hours, and we can see that at the surface the water content is increasing, or the head is increasing. And we might also be interested in the water content, so we can switch to that, and here's what the water content profile look like, somewhat similar to the hydraulic heads. And we've got a variety of other things that we might want to plot, but let's just be content with that for now. The other thing though that we might want to see is up at the surface some time series of the what's happening at the surface. So we can plot, let's see, the actual surface flux at the ground surface. So this is 1 centimeter per hour. That's the rainfall rate. So that's what we expect. We set the rainfall rate equal to 1 centimeter per hour, and that's what we get. And so let's see, surface pressure head. Here's the surface pressure head. As this rainfall falls on the soil, then the pressure head is increasing, and we can see it increases with time, and steadily increases, but it always remains negative. So this is a problem that seems to be fairly common with Hydrus1D, that it crashes, and I'm not quite sure what the cause is, but you just need to be aware of this. Probably need to save your programs fairly often. I'm going to just close this and open it again. And then I can go back to this file that I just made. Test case. And you can see here that we've got the results that have been saved. So that's pretty convenient. It's obviously not convenient that it crashes like that, but convenient that we still have these results and can get back to it pretty quickly. So, no problem. And what we see also here, we plot the surface runoff, and there's no surface runoff for this case. All right, so those are some examples, and that's, I think, our first setup for Hydrus1D. So let's see, that's KSAT is going to be greater than rainfall. So let's go and do an experiment where we boost the saturated hydraulic conductivity and repeat this. So in order to do this, we go to the soil hydraulic parameters. That's where we entered the hydraulic conductivity, and we go there. And remember, we have a rainfall of 1 centimeter per hour, so let's drop the saturated hydraulic conductivity to 1/2 centimeter per hour. And then we hit next, keep all this stuff the same, and we don't want to redo the profile. We don't need to do any of this. So we could hit next. If we hit next, then it's going to ask us if we want to run Hydrus. Let's hit OK instead, and we can then go to calculation and run Hydrus from up here. So when we repeat this, we'll save the input data. Yeah. Okay, so we can hit enter. All right, so now let's take a look at the results where we've now changed the hydraulic conductivity. We've reduced the hydraulic conductivity. So we can see now that the infiltration depth is only 30 centimeters. With the higher hydraulic conductivity, it was 40 centimeters. So that seems to make sense. We can take a look at the water content, and we get this result. I think if we look closely here, we can see that the water content, see that flat place right there? That's the saturated water content of 0.43. So in this example, the soil becomes saturated sometime between 4 and 8 hours. So that makes sense. That's what we're expecting to happen when the rainfall is greater than the saturated conductivity. But notice it doesn't happen right away. We have to have some rainfall falling in order to boost the water content before that really occurs. So let's take a look at the time series and see if we can see that effect. So let's go to the surface pressure head. That should show it. Yeah. So here's the case. It rises up, and remember when the soil permeability or the conductivity was a bit higher, this curve went up and kind of stayed less than 0. But now we can see at about 4.5 hours, the surface pressure head goes to 0, and so that's when saturation would occur. We could also take a look at the Let's see. Okay, so we have the pressure head. I think the surface runoff would also be good to see. So here's what happens with the surface runoff. Right here, after 5 hours, that's when the surface becomes saturated and the rainfall, the flux into the surface becomes less than rainfall, and so this is then the additional rainfall that cannot infiltrate into the soil that runs off. Okay, so that's all consistent with our expectations, but nevertheless, it's really good to see that that's what's happening. Okay, so it looks like we need to revive Hydrus1D again. And we'll go back to, there's our well, that's not it. Go to open. We need this one called test case. Okay, so let's just check and see. This is the example that we were just looking at. So that's good. Now what I want to do is see what happens when we extend the analysis to include some time after rainfall. Okay, so let's see. I'm going to go back, change the soil hydraulic properties right here to 2. And so it'll go back to the original analysis. And what I'm going to do now is say, well, okay, let's say we have a rainfall that lasts for 8 hours, and then the rainfall stops, and we're interested in looking at how the water redistributes after the rainfall stops. Okay, so that'll be the case for this second case where what happened, where basically we address what happens after the rainfall stops. So let's see, let's hit OK there. And what we're going to do is change the time of the simulation, and we'll go out 16 hours. So we'll double the time. And we'll change the print information to, we need to take a look at another time. So we're gonna have look at all the times that we have been looking at, but we'll have one more time that will have be at time 16. Okay, so we added another time, and the default was just to put that next time, time number 6, at the end of the simulation. So that's good. That's what we want. And then we need to include. We basically need. Let's see. Let's hit OK. And so now what we need to do is change the boundary conditions so we have it rain for 8 hours, and then we'll have no infiltration for 8 hours. So go to variable boundary conditions, and we need to add a line here. Okay, so the first line will have go from 0 to 8 hours, and the precipitation will be 1 hour, 1 centimeter per hour. And then the zero, the starting at 0 isn't really shown, but the default, what's implied is that in this time column, the row 1 starts at 0 and goes to this time, and then in row 2 it starts at this time and goes to this time. So we'll put in 16, and then the precipitation is 0. And let's just say for now that the evaporation is equal to 0 as well. Okay, so that'll give us a period of rainfall of 8 hours and a period of no rainfall for 8 hours. And we're going to have one more profile that we add to show what the effect is. So we hit next, and we don't really want to run the profile application, so we can hit next. and this will ask us to run this again, and we can save the yes, and we'll delete all the previous output. So calculations finished successfully, and we hit enter. And now we can go take a look at the profile information. And here's the new curve. Okay, so what's happened is the rainfall has stopped right after this pink curve, and the soil all up here from this point upwards, so from about 30 centimeters up, the water starts draining out of those pores, and that water then moves down and starts filling these pores. So the water continues to move down after the rainfall stops. That water is redistributing, and it does so by draining the pores up here and having the water move downward and start to partially fill at least these pores down here at depth. Okay, so that makes sense. That's the water redistribution process, and that happens as a result of gravity in the absence of the rainfall. I think this problem with Hydrus1D crashing like this, I think that it's going to be specific to your computer, and hopefully my computer is just particularly ornery, and you'll have better luck with this. But as you can see, Hydrus1D has you save the program fairly often, and so we can go and restart it pretty quickly. Okay, so what we've got so far is rainfall redistribution, and now let's go one step further and add in some evaporation. Okay, so that'll require an additional modification, and what we'll do is extend the analysis. So we'll go from 16 hours to, say, 40 hours, and we'll hit next, and we'll need another, let's put in 2 more print times, so we'll have 8 print times. And let's see, so it goes from 16, there's the last one is 40, so that's what we want. Let's make 7, I don't know, let's make it 30. So then we get 2 snapshots during evaporation. All right, that makes sense. This stuff stays the same, the iteration criteria, all this stuff stays the same soil, same boundary condition, but here's where we're going to need to change things. So we really have 3 periods now. We've got rainfall, and then we've got a period after the rainfall for 8 hours when there's no evaporation, and maybe this is at night, and all the water is the rain has stopped, but the humidity is really high, so there's not really any evaporation and no additional rainfall. But then the morning comes, sun comes out, we start to have some evaporation, the trees start to be active. So let's go and add in another line, and we've got to set these times up right. So this is going to be 8, 16, and this will be 40. And the precipitation will be 1 centimeter per hour, and then 0 and 0. And we'll need to add in some evaporation here. So let's make an evaporation rate of that. Evaporation rates are pretty small compared to the rainfall. So 0.01 centimeters per hour for the evaporation. And let's see. Well, I think we could make it a little bit bigger than that. Let's make it 0.05. And let's see. Next. We'll go next, and next, and then we can run it. So we'll save it, run it, There's the results, and we can take a look now at the profile. Okay, so here's what we got. These two are our next two curves, and you can see that we have the water continue to move downward. It's moving down past the bottom of our model after 40 hours, and we also then have the water trying to, or the water content decreasing pretty rapidly here as a result of the evaporation process. So we're having upward flux from evaporation. So there's the pressure head, there's what the water content is looking like, and the water content, if we integrate this curve right here, the area under that curve and the area under this curve, they should be the same because we haven't added any water or removed it. But now for these curves, we're starting to remove some water, so the area under these curves actually is going to be less than the area under this curve and this one. But we can see this redistribution process. Okay, we could also take a look at the flow at the boundary or up at the top, and here's the potential surface flux. So we have infiltration of 1, that's the rainfall, then 0, and then this is the evaporation. Okay, and we can see the evaporation. We also might take a look at the, let me see, surface pressure head. There we see the pressure head rising and then falling, and right there is where it switches and we start to have evaporation, so the pressure head is falling even faster. Let's see, we can also take a look at the surface runoff. We don't expect there to be any though, right? Because the surface has never become saturated, so that's good. That's consistent with what we expect. And let's see. Okay, the actual surface flux is going to be there, pretty much the same as what we saw for the potential. Okay, so very good. That's the example with rainfall and then re-equilibration from gravity initially, and then from gravity with evapotranspiration. Okay, now our last example will include a layer, soil layer that is got a lower hydraulic conductivity. Okay, so what we'll do is just stick with this baseline model, and we'll modify it to include another soil that is going to have a different lower hydraulic conductivity. So go here to geometry information, and we want to have 2 soil materials. So we do that and hit OK, and the time information will be the same. And let's see, the whole soil hydraulic parameters. Now we see, as a result of changing the geometry information, we get these 2 different soil materials that we'll put in, and it'll be material 1 and soil material 2. So what we'll do here is just for our purpose here, we would probably have different, all of these would probably be different if we have a different soil material. But what I'm going to do is just change this one, and I'm going to change it to 0.1, and that's just so we can see the effect of having a low permeability layer. So hit next, and all this stuff will stay the same setup for the time, but now we do want to run the profile for this one. So we'll hit OK, and we'll save the data just in case it crashes. And okay, so now we go back here to this editor, and I want to set up the soil layers. So go here to conditions and material distribution. And the way I've set this up, if you'll take a look at the notes, this layer will be between -20 and -30 centimeters. So if you look down here in the lower right, see Z, that's the position of the cursor. So as I move it, you can see right now I'm at 44.8, -44.8 centimeters. Okay, so up here there's 0, and then it becomes more negative as you go down. So this soil, this layer number 2, is going to be at between 20 and 30 centimeters depth. So what I'll do is go and put my cursor over here in these horizontal lines and go to 20 centimeters, and there's 20, and then oh, okay, sorry, got to go here to edit condition. Now go over here to minus 20 and then drag it down and see how it changes from green to yellow. That means that you're making the selection. So just hold it down, green to yellow, and then go over here and left click. Okay, and we change the material index, so this is now going to be material number 2. And there's should show up as blue, and you can see over here there's the blue is 2 and the red is material number 1. Okay, so we could put in more materials, but I'm just going to assume that we've got this low permeability layer here at 20 centimeters depth, and everything else is layer number 1. Okay, so we save changes, yes, and hit OK for that. And now we go here and we can just check. See, here's matte, that's the material, and if we scroll down, yeah, so right there under Z of 20, you can see we switched from material 1 to 2. Okay, so that verifies that we've made the change the way we wanted to, and we'll hit next, and this allows us to run. So there it runs successfully, and we hit enter, and now we take a look at our profile. Okay, so now look, we get this kind of sharp kink here, and we also see a bit of a change right there. So this is the top of the layer at minus 20 and the bottom of the layer at minus 30. And let's see, it'd be nice to make this bigger. Not quite sure. One thing we could do, here's a way that we could make it bigger. I'm going to go and copy it, and then I'll go here to Word, and here's just this file. I'm just going to paste it in this file. So there's the figure that we just copied and pasted into Word, and so this gives us a way to get it into a document. So let's take a look at what's happening here. So the first 3 profiles right here, the blue, the dark blue, the green, and the light blue, those are the same. Those are the same that we ran from the very first scenario, because it hasn't gotten deep enough to interact with the layer. But now this one, I don't know, it's orange, I guess, orange or red. You can see it curves, and then it becomes steeper here. That's because it's being impeded by this low permeability layer. And what happens then is that as it gets impeded by that layer, the saturation increases, and then the blue layer is got a hydraulic head of greater than 0. So at this point, this whole layer above the low permeability layer, this whole surface is going to be saturated, and we even have positive pressure. So this is like a little perched water table zone. Okay, but then the rainfall stops, and we start to get redistribution. We still have the water moving down into the underlying layer, somewhat impeded. We've got this change in the profile, and then evaporation shown here in these last 2 profiles that we get during evaporation. Okay, so that looks good. We're starting to get some complications, but we see this effect of having this low permeability layer impeding, causing saturation. And if we go back to Hydrus, we can see the effect of this. If we go to water flow, here's the potential flux, but if we go to the actual flux, so you can see here now that the actual flux ends up being here a little bit different. And that's because once the soil becomes saturated, right in here, the flux during the rainfall, once it becomes saturated, the flux is going to drop, and we're not going to have as much flux into the soil as we expected. Well, we're not going to have as much flux as the rainfall is providing, and so that's what we expect when saturation occurs. And so what we might expect also is that some runoff is going to occur in this case. And let's go to surface runoff. So there it is, and we can see that just with the way we have this model set up, we get some runoff. I don't know, it looks like for about an hour, right at the end of the rainfall, as saturation occurs, and we've got the upper soil layer becoming saturated and triggering runoff. Okay, so that is the tour through Hydrus and these different examples. You can see that there are a variety of different types of output that we can get to try to tell the story about what's happening as the pressure changes and saturation changes during the infiltration process, and following it as water becomes redistributed. So this will give you an introduction. There'll be a variety of other things that we can do, but this will be a good place to start.